Welcome to my channel Math Physics Academy. We started electromagnetic induction and we discussed basics about electromagnetic induction. We also discussed Faraday's law of electromagnetic induction, the various experiments conducted by Faraday, the mathematical formulation of calculation of induced EMF, that is epsilon is equal to minus d phi by dt, including Lenz's law, which gives the direction of induced EMF and induced current. That was in first video of electromagnetic induction. In second video, I solved two basic questions, but which needs conceptual clarity. That type of question I discussed, and in continuation to discussion on little more advanced questions, or you can say good questions, which can come as 3 marks or 4 marks, we are going to discuss now. Let's go to the question. So this is the question. When a conducting loop of resistance 10 ohm and an area of 10 centimeter square is removed from an external magnetic field acting with time as shown in the figure. Okay, so let me make the figure first. So the figure is given to us in x and y axis. In x axis, time t in second it is given, and in y axis we are given current in ampere. We are also given that this is 0, 0, and this is the point A, this is point B, and this is point C. We will join this point, and this is given as 0.4. Okay. And this is given as 1.0. This point C. Point C is 1.0 and point A is 0.4. Right. This is the figure. So as shown in the figure, find the total charge passed through the loop. We need to find total charge. We need to find change in magnetic flux through the loop, and we also need to find magnitude of the magnetic field applied. Right, magnitude of the magnetic field applied we need to find out. Okay. Let us solve it. Solution. So first one, total charge passed through the loop. So we know that the relation of a current, that is called I, is dq by dt, right? The charge passing through per unit time is called current. So from this relation, we will be in a position to find out dq, total charge, is equal to I dt. Okay, I dt. So dt is the variation. Now this I dt is what? So area. Now we can say that total charge dq can be found as, because it is shown in figure, so it is magnitude of area. Magnitude of area of the figure given. So this is triangular figure. So we can say that area of triangle ABC will give us as the total charge. We know that area of a triangle is equal to half base. So this one will become base, and this is height. Half base into height, because it is a right angle triangle. Okay, so half base into height. Right. Even if it is a right angle triangle or any triangle, the area of the triangle is half base into height. But in like equilateral triangle, we need to find the height. In isosceles triangle, scalene triangle, we need to find the height. But in right angle triangle, its vertical limb itself, AB itself, it is the height. Anyone we can take it as base. AB we are taking it as base, then BC will become height. So it's easy. Right. So from this area of the triangle we will be finding. So half base. So what is the base variation? 1 minus 0. So this is the point C and this is the point B. So BC will be equal to 1. So 1 into again height. So 0.4 minus 0. Okay, it is already in ampere. So 0.4. Okay, right. So 0.4. We will cancel it with 0.2. So total charge passing through the loop is 0.2 coulomb. 0.2 coulomb. Yes, here point is there. 0.2 coulomb. Fine. Now coming to change in magnetic flux. Change in magnetic flux through the loop. So second. Now we know that dq is equal to I dt. Right? Now I. We know that I is equal to epsilon by R, that is EMF by resistance. Okay, and EMF is equal to what? d phi b by dt. So we can write in place of I. So I will become what? I can be written as d phi b magnetic flux. Okay, and R dt, R is there, so R dt. So in place of R, we can mention as d phi b by R dt into dt. So this dt and dt will get cancelled, and we can get from here d phi b means change in magnetic flux is equal to R into dq. dq already we found, so d phi b, that is change in magnetic flux. R is given as 10 ohm and dq is 0.2. So this will be equal to 2 Weber. 2 Weber. Weber is the unit of magnetic flux. 2 Weber. Now third is magnitude of magnetic field we have to find now. Okay, magnitude of magnetic field. So that we will be finding it out. We know that d phi b is equal to b dot a, and which can be written as BA cos theta. So as it is written that the loop, conducting loop is removed from an external magnetic field acting with time. Okay, so in that case theta will be equal to 0. Theta will be equal to 0 degree. Due to this theta will be equal to 0 degree, cos 0 will be equal to 1. So we can write d phi b is equal to b, magnitude of b, and magnitude of a. Further, we can write b is equal to d phi b by a, and d phi b already we have found, that is 2. So 2 divided by area. Area is 10 centimeter square. So once area is equal to 10 centimeter square, we can convert it into 10 power of minus 4 meter square, which will be giving you 10 power of minus 3 meter square, right? So 10 power of minus 3. So we can write it as 2 to the 2 is equal to, so magnetic field will be equal to 2 into 10 to the power of 3 Tesla, right? It is magnetic field, so we can write 2 into 10 power of 3 Tesla is the magnetic field. Right, going to another slide, another question. Yes, it is also a very good question. Right, so a square loop of side 20 centimeter. Okay, so let us make that loop itself a square loop of side 20 centimeter is initially kept 30 centimeter away. It means at a distance of 30 centimeter away from a region of uniform magnetic field. Okay, from a region of uniform magnetic field. So let us make it as here for a region of uniform magnetic field. Okay, and that magnetic field also, it is given in the question that it is of length 80 centimeter. Okay, we are not going to utilize that, but this is the uniform magnetic field. So uniform magnetic field of 0.1 Tesla as shown in the figure. So side 20 centimeter, we will convert it into meter. .2 meter, and 30 centimeter, that 30 centimeter will be equal to 0.3 meter. Magnetic field already it is given to us as 0.1 Tesla. It is then moved towards the right with a velocity of 10 centimeter per second. So it is moving with a velocity of 10 centimeter per second. So 10 centimeter per second, so velocity is equal to 10 centimeter per second, which can be written as 10 centimeter means 10 into 10 power of minus 2, so 0.1 meter per second. Okay, 0.1 meter per second it is. Okay, so we have to calculate some of the things. Like first, it is given magnetic flux through the loop with time t. We have to plot a graph. Before plotting a graph, we need to find out that magnetic flux, magnitude of magnetic flux we need to find out. So how we will be finding out that magnitude of magnetic flux? So it is, we know that magnetic flux phi b through a loop will be B dot A. Okay, it is B dot A. So here area is L into X, L into X, area Lx. So that area of this loop itself, square loop. So magnetic field is given to us as 0.1 into side is given 0.2 because it is a square, so side is square only, we can write as area. So 0.2 into 0.2, right? Okay, so it will be equal to 4. Okay, so it will be equal to 4 into 10 power of minus 3 vapor. So because it is moving right and goes out of the field, if it is going out of the field, so you can say that phi 1 is 4 into 10 power of minus 3, which will be constant till the time that square loop will be in the magnetic field, and when it will go out of the magnetic field, that phi 2 will become 0. Okay, so it can be plotted in this way, and here time in second, and here phi in vapor, and it will be given the point maximum, it is 4 into 10 power of minus 3. So it will be increasing from 0, then it will be constant till the time this magnetic field is there. Okay, and then it will reduce back to 0. Okay, so in this way we can plot the graph where we can show the variation of magnetic flux. Second, induced EMF in the loop with time. So now we have to find induced EMF. So we know induced EMF in the loop with time t. Okay, so induced EMF epsilon is equal to minus d phi by dt, is equal to minus d phi by dt. Here, because the loop is moving with the velocity, so it will be having motional EMF, and motional EMF is BLV. Motional EMF is BLV. Now, magnetic field is already given to us. Okay, and L is also available with us, that is 0.2, and velocity is also available with us. So we can find maximum EMF magnitude as 0.1. It is 0.1 into L is 0.2 into V is 0.1. So it will be 2 into 10 power of minus 3 volt. Okay, 2 into 10 power of minus 3 volt. So now this also can be plotted in this way, time in second, and here EMF in volt, and both will be there, positive and negative. Okay, so minus 2 into 10 to the power minus 3, and here plus 2 into 10 power of minus 3 both will be there. So initially we can say that it will be varying with the minus, and then when it is entering into the field and then when it is going out also like this can be plotted. Third, induced current in the loop. Now induced current we need to find. We already found that maximum EMF. So induced current I is equal to magnitude of EMF by R. Magnitude of EMF is 2 into 10 power of minus 3 by resistance is given as 0.1 ohm. So it will become 2 into 10 power of minus 3 and 10 power of 1. So it is 2 into 10 power of minus 2 ampere. Okay. This also can be plotted similar to the EMF. So like this it will be there. Okay, again T in second and induced current I in ampere, and it will also have both value, that is minus value also, minus 2 into 10 power of minus 2, and plus value also 2 into 10 power of minus 2. Okay, and it will also vary similarly, and here it will be varying positive side. So in this way we calculate all magnetic flux, induced EMF, because here the loop is moving in the magnetic field, so it will be taken as motional EMF. That is, motional EMF is BLV. V is the velocity of the loop. Fine. Similarly, we will be solving many of the questions in the coming days. Thank you. Thank you.